Okay. So this morning I wanted to correct one definition and introduce one other notion, and then talk about some of the challenges that remain. Again, this is just for good fun. So before, in the previous definitions for the outer product, I had set this to be the name of Q times X, where X ranges of the free names, in the name of P times Y, where Y ranges over the free names of Q. But that doesn't actually respect this identity. It's a little bit, it's off. But if you set W equal to the name of P par Q, then you will get that, because if C is multiplied by P, then
yeah, Greg, I'm not sure if you meant to share the screen, but you at least I'm not seeing the screen.
Oh, okay. I thought I had turned it on, but I'll redo that. All right. So again, the idea before had been that if we take the name of Q times the free name times each free name of P, and the name of P times each free name of Q, and that will end up leaving the C in one side or the other, which is not quite what you want. However, let's say you have C times P, right? Then the C will be in here, and now you'll get C times P par Q, and the name of that, and that will be multiplied by all the names in X, right? And all the names in Y. Now, if you have P par C times Q, well, we showed that that's the same as just putting the C over here. So again, we get, so what's now on the nose equationally equal. So is that clear? Because it'll be, the W will be the same in either case, and so now you're having W multiplied through, and so you'll get exactly the same process no matter what. Is that clear?
It makes sense.
Okay, cool. Now there is one other approach to this which I want to just point out that's kind of interesting. Instead of reifying P and Q, which shifts us up a level, you can consider a more matrix-like operation where you think of each of the free names in P as like an entry in a vector, and each of the free names in Q is like an entry in a vector. So you think of it as like a row vector and a column vector. And then you multiply, let's say X is a free name in P, and you multiply X by each of the free name, each of the Y's in the free names of Q. So that's going to give you one name, and then you substitute that, and you go down the X's that way, and you go down the Y's, in the converse fashion, and that will also get, but then you turn it into a big sum. So you sum over all of those, and that's more matrix-like in its behavior. I haven't checked all the equations, but that's another approach which keeps you kind of, you don't lift up to the P and Q level, right? You stay down one level down from that. So that's an interesting approach. Notice that before they would end up in separate namespaces, so there would not be any interaction, simultaneous interaction, and this mixes the two namespaces. So that's a better outcome in terms of wanting the intuitions about how processes interact to line up with how interaction in quantum mechanics works. So hopefully that's clear. That was a little correction I wanted to make, just to be clear, just to make sure that the identity is respected. And it also turns out that what I didn't present before was a notion of superposition or summation, right? So the typical qubit is going to be some, some alpha times, let's say the state 0 plus some beta times the state 1, representing some binary choices in states. The cat is alive or dead, or the spin is up or down, that sort of thing. And it turns out that you can get some of the properties lining up. So if you pick summation as the definition, so summation of processes. So this is like choice, but we're going to allow for mixed summation. So you can sum over outputs and inputs, which is more expressive, right? So again, referring back to Palamadisi's results, there is no par-preserving translation of mixed summation down into the asynchronous version of the calculus. So that's interesting. It's now saying that there's something more going on with par as soon as we make this choice. And you can check by definition that this satisfies the distribution of multiplication of scalars, because we're just going, all the free names in P are going to be substituted by X times the free name, and all the free names in Q are going to be substituted by X times the free names. And that's the same as if you did this and then did the summation. So that's that identity is satisfied. So we can represent, things like qubits. Now, the one thing that's more tricky is quantum interference. So if I were going to multiply by minus beta, then it's not clear what the minus sign refers to. You kind of like it to be so that you flip inputs for outputs, or something like P par minus P is equal to 0, but it's not that, because we're talking about summation, right? So this is sort of a choice between outputs, or a choice between inputs. And so what you want to do is, if you multiply, if you add the minus sign, then it needs to take away those choices, remove the choices that P offers. There is an approach that I've thought about for a while, but it's kind of out there. So you think about it not in terms of 0, but in terms of divergence. So divergence is sort of like the big quantum foam. It's all actions are possible. So you can think about P, and minus P is offering everything, every possible action that P doesn't offer. So when you sum P and minus P together, you get divergence, right? It's sort of the divergence. The negation of P is the divergence take away all the things that P could do. So you carve that out from the divergence. And then, so it's not completely, so minus P is not completely divergence, right? Because you're removing all the P actions, whether they're input or output. And in time even, right? So you're taking away throughout the lifespan of P, and that will so that will be not quite divergence. It's sort of like kind of like a notion of a set complement, only these are sets extended in time, or probably closer to say relations extended in time. and then P puts those back in, right? And then so when you put them back in, that plus divergence minus P is going to be divergence, and that'll give you a notion of an additive identity that's not the same as the multiplicative identity. And it's interesting to see whether or not that lines up with the notion that you get from in quantum mechanics. So that's for future research, but it does have some of the nice properties, right? So you'll still get distribution by of multiplication by scalars. I haven't checked whether the divergence thing interacts nicely with the outer product. And I need to think about how it works with the inner product as well. So there's still a lot of checking to do, but it does give you some kind of coherent notion of an additive inverse. So let me just stop there and see if people understand what I'm mumbling on about.
So can we say that if P is something that is receiving on X, then minus P is all the other processes that are not receiving on X?
Yeah, it's the summation of all the processes that are not receiving on X, exactly.
Okay.
Yeah. So obviously when you put P together with minus P, then now you have all possible actions, and so you have divergence. And that I'm not terrifically satisfied with that yet, but but it's still early days. Yeah. So anyway, I think that was I just wanted to make sure that I corrected that and that I mentioned this idea. Now, the interesting point is that even with this much, we can still represent qubits, right? In fact, we can go a little bit further. We have a notion of nth root, right? So my root talk. So obviously you could do quantum mechanics in projective space, and so you don't normalize everything. And so that's we don't necessarily have to have that to do interesting quantum-like things, but you can actually write down states like the square root of 1 over the square root of 2 times the 0 state plus 1 over the square root of 2 times the 1 state, which will give you equal probability distribution over the 2 different states in normal quantum mechanics, and we can give an interpretation to that in this setting, and that will we can check to see whether from an intuition point of view that lines up with what we might think of when we're doing ordinary quantum mechanics. So that's to me that's how do I say, it's interesting that we can get to that level of detail. Yeah, that's all I've got this morning. It was important to me to make that correction and then talk about this idea of being able to represent summation and talk a little bit about what the challenges are. So any questions about that?
Yeah, this is very, very interesting, and it's difficult to understand two things simultaneously, right? You're talking about quantum mechanics, which I don't know, and you're using row calculus in a way that also I'm trying to understand. So
Yeah, understood. Understood. Yeah.
Can I ask you in a more general way? So, do you think about when you want to apply, when you are developing this kind of representation? So you're using namespaces and names to encode something. So can you maybe say something about your process of designing this thing? Uh,
Yeah, well, in this case, things are really, really well defined, right? Quantum mechanics has very, very specific identities, right? So I have to respect an identity like this, right? That comes from quantum mechanics, and so I have to make sure that whatever definitions I put forward, those definitions match the axioms of quantum mechanics. All right, so yeah, that's kind of the idea. I mean, you can do things. Um, Ultimately, what I would like is for the ladle types to represent a kind of design language, right? So that when you're designing things, you design for software purposes, you design things at the level of types, and then you go about looking for processes that are going to satisfy those types. Um, right. So for example, if you were designing a voting system, um, there's type information around, right? Like you don't like no voter gets to vote twice on this, gets to cast the same ballot twice, for example. So you can write down that what that means at the type level without committing to an implementation. Then you can write down other things like no other voter gets to see the results of the ballot of like no two voters get to see the results of each other's ballot. That's a type level assertion, right? It doesn't say how you do it. It just says that that's a fact about voting. So you could write down everything that you want to hold true of the system at the type level, and then go about looking for row implementations that will satisfy those types. So that's one design mechanism. And that's kind of like what I'm doing here, in the sense that there are laws that I have to verify. Like here's a law that I have to verify. You know, here's a law that I have to verify. So those are type-like assertions. They're not quite the same as types, but they're type-like assertions in the sense that they're governing. These are equational schema, right? It's not a specific U and a specific C and a specific V that this holds for. It holds for all U's, V's, and C's. And so when I come up with a definition, I need to check that definition satisfies this equation, and likewise, this has to satisfy that. So again, this idea of design by type is one that I follow quite a bit.
Makes sense.
I guess I would say that, I certainly don't understand quantum mechanics. I don't think that very many people understand quantum mechanics. A lot of people have operational understandings, in the sense that, you set them a word problem and they can solve it. As long as the word problem is within certain parameters, they can solve it using the linear algebra that's associated with quantum mechanics. But that's not the same as really understanding quantum mechanics. And likewise, there's still lots and lots of things about the row calculus that I don't know, that I don't understand, right? It's like just because someone knows the rules of Go doesn't mean they understand the game, right? They don't have a feel for the implications of the rules. And so I have a certain level of feel for the implications of the rules, but by no means would I say that, I've gone beyond scratching the surface. I wrote down what I knew they had to satisfy in terms of, certain kinds of constraints. that we knew about computing in general, and that we knew about process calculi and so on and so forth. So, but that doesn't mean that, because I have those insights, that I really have a deep understanding of that calculus, right? That comes from years of use of it. Um, and but when you try to line up two different computational frameworks like quantum mechanics and the row calculus, then you learn about each, right? It's, by trying to encode one in the other, you learn about each. It's like my friend Brian Beckman used to say, well, the way I learn a language is I learn two languages at once, and I write a compiler or an interpreter from one into the other.
Yeah, I
Right.
remember your conversation with Brian Beckman on
Ah,
Channel 9, I think.
yeah,
Yeah,
that's right.
I think that was the first time I saw you. So
Ah,
yeah,
okay.
that was very interesting. You were talking about locations, and I mean, both of you were talking about locations, and yeah, that was super interesting for me.
Yeah, well, I still think that there's a lot. I mean, I've gone a lot further than that because I have the space calculus now, so I can actually, I can compute with the notion of location like that. But I think that that's a much deeper idea. And again, I think that, it's sort of like what we were just talking about in the sense that, you know, Ue wrote down this idea of location in a tree, and then, posited that it might work for a wider range of data types. Connor McBride shows that for a very broad range of data types, that idea works. Um, and But neither of them really understand the connection between that and data kind cuts, right? And so when I saw it, because I'd studied Conway games and data kind cuts, I looked at it and said, wait a minute, this looks like a very natural generalization of that idea. Um, and I still believe that this is a, you know, gives you a really good notion of location. And I've been able to justify that to a certain extent because the space calculus does what it does. Um, but it would be, it would be fantastic to be able to give a real number like a real number like expansion of that idea, right? So um, how, how do I say this? So you think about the data kind or the Conway games are easier to see when you allow for infinite structures on the left and the right. Then that's when you start to get, real number like gadgets, right? So you have a notion of location in a tree with the zipper, um, but imagine that you allowed for infinite sets of things that could fill the top, the the context, and that could fill the whole, right? Um, so then you'd get uh, oh, that's really interesting. I hadn't thought about that. That's very interesting. Yeah, so you could take the Conway notation, but instead of just having it be games, you have it be contexts and things that fill the whole. And so now you get sets of devices, sets of gadgets, right? And as soon as you allow for infinite things to fill the whole and infinite context, then you get an analog of your real numbers, and that might give you, um, something that something that you can do normal, or how do I say it? Not normal, but something that's closer to the kind of differentiation and integration that we're used to from Newton's calculus, right? So that's an interesting. I mean, but that was the insight that I had, and again, the point is that, you know, as mathematicians, we're, you know, frequently just scratching the surface of these definitions that we give, right? When it takes a long time to kind of work with them, and part of the way I like to work is by connecting, you know, one whole system to another whole system and see how they relate to each other. And that's to me, that's an important process, because it's you know, it sort of is intended to respect and elucidate what's whole about each system, right? What makes quantum mechanics cohere, what makes the row calculus cohere, you know, what makes Conway games cohere, right? That's the idea. Awesome.
Thanks for
Thank you.
explanation.
No, I appreciate the question. Well, I'm going to give us a good 30 minutes before stand-up. So I will see folks in Dev stand-up in about 30 minutes.
Thanks.
Great. Thanks, Greg.
See you.
Ciao, ciao.
Bye-bye.
Bye.